Hello. Today I want to talk to you about reactive oxygen and reactive nitrogen species, the so-called RONS, R-O-N-S. What they really are, why they matter. They're widely quoted in application of electric discharges in medicine, so plasma medicine, but they're also important for all sorts of atmospheric pressure, plasma processing of different surfaces in room conditions. I also want to separate chemistry from hype and give you kind of a systems level perspective on this. So a little bit about me. I have a PhD in bioengineering. I spent over a decade as university faculty and then founded my own company to commercialize plasma applications. And I've been doing that for almost a decade at this point. The focus of my research is atmospheric pressure in non-equilibrium plasmas and their applications in medicine, environmental remediation, destruction of forever chemicals, surface cleaning, etc., 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 etc. So if you enjoy deep, calm, scientifically grounded conversations, this channel is for you. If this is your first time here, welcome. Again, my name is Greg Friedman. It's a pleasure to have you. And if you like this content, click the like and subscribe button. I publish these videos every Tuesday, Thursday, and Saturday. Happy to see you. So, what does it mean, reactive species? Well, they're chemically unstable reactive molecules or atoms. Typically, you would see them produced in plasma. It's pretty difficult to produce them by other means. And plasma is very good at ionizing different gases and producing lots of different kinds of reactive species. Those range from reactive metal ions to all sorts of chemically unstable and highly reactive atoms and molecules. And generally, these are atoms or molecules with an unpaired electron, so they're ready to react. These are high energy states. So it's a high energy system, and reactivity of the system is driven by thermodynamics and chemical kinetics. So what are some of the reactive species we might see? Well, in air plasmas, the most common species that we talk about, and the ones that I think are the most important, are reactive oxygen species and reactive nitrogen species, and together they're called RONS. So with oxygen, well, you have O2, which is a stable molecule in atmospheric conditions, thank God. But that molecule can be broken into two halves, so you can have atomic oxygen. Well, first of all, actually, let's start from the very beginning. So you have so-called singlet oxygen, or electronically excited oxygen. Already, that molecule is far more reactive than just ground state normal oxygen. And let's say you need oxygen for flames, so it's oxygen oxidizing wood. And if you have singlet oxygen, that process will just go so much faster. So if you need to clean the surface or you need to increase rate of oxidation, singlet oxygen would do the job better than ground state oxygen. But that oxygen molecule can break into two atomic oxygens, and that one's even more reactive. Or it can absorb an electron and become what biologists call superoxide, O2 minus. It is biologically a very important molecule because your own immune system uses it to fight infection or control inflammation. You can also break down water. So take water, H2O, and rip off one of the hydrogens. You're left with atomic hydrogen, which will reduce any molecule it comes in contact with. You also have OH radical, which is highly reactive, especially with organics. Its probability of reaction is close to 1, meaning when it collides with an organic molecule, it reacts immediately. As a result, though, it's a very short-lived molecule. So the more longer-lived ones would be something like hydrogen peroxide, which can exist in atmospheric conditions for minutes to even sometimes hours, depending on how it's preserved. You have ozone, which is very long-lived, not very reactive, and also ozone has kind of a bad rap with Food and Drug Administration, so ozone-producing systems aren't the most popular, though I do think it has a bad rap. I think there is more to it than just bad molecule. And for biological effects, the lifetime of these things is highly important. Most of the time, you can't make plasma somewhere else and put it in a bottle so you can deliver it and buy it at the pharmacy. There are, though, few and rare exceptions. For example, you can use reactive oxygen species to peroxidize longer chain organic molecules, and then that you can put in a pharmacy. Shelf life can be months or even years, but those aren't as reactive as freshly made, juicy reactive species with lifetimes in nanoseconds. Well, then you have reactive nitrogen species. The most popular of them is nitric oxide, and it was a molecule of the century, last century, where a lot of people in molecular biology believed that NO, nitric oxide, is the molecule that your immune system uses for signaling and attacking bacteria. Today, the belief sort of shifted a little bit to combination of nitric oxide and peroxynitrite. So nitric oxide that reacted with superoxide anion, and today it is also attributed with action in your immune system. There are other nitrogen oxides, NO2 and 2O3, and lots of them. And the main point here is air is predominantly oxygen and nitrogen and a bit of water. And when you ionize it in plasma, you will have a lot of this N, O, and H combinations of all sorts, and they all have strong and important biological effects. So how does plasma generate them? Well, to put it simply, you have high energy electrons that you accelerated using very high applied external electric field, and when that high energy electron collides with a molecule, it transfers some of its energy to that molecule, ionizing it, breaking it down, leading to dissociation, excitation, ionization, and formation of these reactive oxygen and nitrogen species. There are also cascading secondary reactions where not just electron does the job, but the ionized or excited molecule goes to react with other molecules. And those can actually go into chains and go into tens or even hundreds of reactions. What's important here is your output, your product of your plasma, depends very much on what gas you're using. Like, for example, if you're doing this in, let's say, a farm environment where you have a lot of volatile organic compounds, poop smell, your plasma will contain different reactive species than if you're using it, if you're generating plasma in a sterile hospital air environment. So gas mixture, very important. Humidity, very important, because very low humidity, you will have lower concentration of OH radicals versus, hot and humid environment. Hot doesn't matter. Plasma itself is the energy, the temperature of electrons, for example, can be in tens of thousands of Kelvin. So plasma doesn't care about room temperature fluctuations so much as it does about humidity. And also, what power you're putting into the system, geometry of your system, all of those play very important role in how plasma generates these runs and what their concentration ends up as. So not all plasmas are created equal. You can't just go to Amazon.com, buy any random plasma machine or plasma machine, because a lot of machines are called plasma while having nothing to do with it, just because plasma is a cool word to use. Like, there is a hypodermic needle used for skin regeneration that I believe is called like a plasma pan or something like that. It has nothing to do with plasma. It's just a hot needle vibrating. And for some reason, they called it the plasma pan or plasma pencil, something like that. Point is, there's a lot of hype, and you have to dig through it. It's more complicated than that. Not all plasmas are the same. Lifetime of the species that plasma generate matters too. A lot of these species, like OH radical, it's so reactive that its lifetime is in nanoseconds. Others persist longer, maybe milliseconds or sometimes even longer. Hydrogen peroxide can live for a long time, seconds, minutes, depends on the environment that this is generated in. And which species dominate also matters. You know, funny tangent. When you start studying plasma, older folks like myself, they will tell you, you will master plasmas when you can smell temperature. You know, plasma, room temperature plasma, generate predominantly reactive oxygen species. As the energy increases or temperature increases, reactions with nitrogen begin to dominate. So low temperature plasma, you will smell ozone. And higher temperature plasma, you will smell nitric oxide. So at high temperature, you produce nitric oxide. At low temperature, you produce ozone. And there's a clear transition between the two. Now, funny, the smell is similar, but different. So you become the master when you can tell the difference between the two, which I find kind of cool. I remember one of my PhD advisors telling me that one day I'll be able to smell temperature. And I was like, nah. And now I'm telling it to you. Anyway, so lifetime of these species matters. And for biological effects, you know, all of these species, these reactive oxygen, reactive nitrogen species, they readily react with all organics, especially tiny bacteria. Bacteria are quite easy to kill. Plasma creates lots of reactive species, electric fields, ultraviolet, including vacuum ultraviolet, which is low, very deep UV, which only penetrates a few hundred micron, but then if you bring plasma in direct contact with human skin, you have vacuum UV right on the skin. So you need to look at effects of that too. Now, the catch is in both dose and dose rate. Now let's talk for a second about the difference. You know, is 1 gallon of whiskey a lot? Well, that's a trick question, right? Like 1 gallon of whiskey yesterday night would have probably killed me. But 1 teaspoon a night, totaling in a gallon a year, well, that's a whole another story. But keep in mind, dose is the same, 1 gallon of whiskey per 1 human. The dose rate is different. And in plasma especially, dose rate is something that you can control with electronics. So you can pulse envelope your plasma system, meaning you have pulses, but you can also put an envelope. So you have 10 pulses and nothing for a while, and 10 pulses and nothing for a while. And that's quite important in many applications, especially in biology, where you need to push mammalian cells over a certain threshold, and then they become active. Like you shake them up, awake, and when they're active, they just do their job. So for example, you can, similar doses that kill bacteria, send mammalian cells, human cells, into angiogenesis, which is like a blood vessel growth or tissue regeneration. So you can improve wound healing while disinfecting the wound. So you treat the wound, you kill the bacteria, and you stimulate the cells. You shake your immune cells awake. Higher doses of these reactive oxygen and nitrogen species put cells into apoptosis, which is programmed cell death. It sounds bad, but it's not. It's like, dying in an explosive car accident versus, your doctor telling you exactly, I mean, that's terrible, but let's say the patient has cancer. So the doctor says, okay, you have 3 weeks to live, put your affairs in order, put everything away. So apoptosis is programmed cell death, where cell undergoes a big series of very complicated processes. Interestingly, cancer cells seem to forget how to go into apoptosis. And for some of cancer types, and this is purely, in vitro, like in a petri dish, we can induce apoptosis in cancer cells that otherwise forgot how to do it. It's just very interesting effects. We can trigger inflammatory or anti-inflammatory effects of plasma treatment on the immune system. And all of it has to do with what type of species you're generating, what type of plasma you're using, and dose rate. So lots of variables to consider when you're selecting the appropriate treatment. To make matters worse, measuring these species can be a challenge. You're talking about low concentration, maybe way below part per million or 0.01% in the gas phase with lifetime of nanoseconds. One of the ways to measure these species is so-called optical emission spectroscopy, where you look at the wavelengths of the emitted light and based on that, try to figure out what species were present when that light pulse happened. You can do very clever tricks with lasers combined with optical emission spectroscopy to try to figure out concentrations of these species. Where things get really tricky is when this is happening at the interface between gas plasma and your finger, for example, if you're treating your finger. So at the very, very interface, the processes change. And the diagnostics, where are you looking at? Because when you're looking at the emitted light, you don't know you don't know exactly where the light came from. Was it from plasma or was it just from that sliver of the surface? So your lasers for this diagnostic become way more expensive and it becomes exponentially complicated. But another way is to inject your finger with chemical dyes. Well, we're not going to use your finger for this. We're probably going to take a petri dish, fill it with agarose media, and mix it with a chemical detector dye or a chemical probe. Plasma treat that dish and then look at depth of penetration and surface distribution of the reactive plasma species that activate that probe. There are things like electron spin resonance and mass spectrometry. They're complicated and they need special dyes and special treatments. It's challenging, but it is doable. That is what scientists do, is they use highly sophisticated, very expensive diagnostic equipment to measure one minute detail. That's why we need a bunch of scientists. And, interpretation of data is also increasingly complex, directly related with the complexity of your measurement equipment. But anyway, I talked a lot about oxidation. Plasma is not purely oxidative. For example, we can generate solvated electrons or hydrated electrons. These are electrons floating in the water, and they're able to provide you with reductive chemistry. There are many reductive pathways. Add a little bit of hydrogen to your discharge, and now, or just run in pure hydrogen. And now you have very different plasmas, so you're able to reduce surfaces rather than oxidize them. It is being able to do that is very important for multiple environmental applications. So depending on what kind of chemical you're trying to get rid of, you're able to oxidize it or reduce it, or a combination of both. Like, for example, with PFAS, the perfluoroalkyl substances, or the forever chemicals, plasma's ability to offer oxidative environment localized temperature effects, and hydrated electrons, all of those play an important role in destruction of forever chemicals. Not just one, but combination of them. It's one of those whole is greater than sum of the parts. So when you put all of those together, the effect is much stronger if you did each one in sequence. Be careful with hype. You know, when you go on Amazon.com and search for, I've done this, like plasma medical device or plasma wrinkle reduction, the claims they're making are crazy. Careful, careful. There are a lot of broad claims without any kind of specificity or even warning that you should not use this in a humid environment or something like that. The mechanisms are often oversimplified, so I am actually thankful. Having worked with Food and Drug Administration, I've gained tremendous respect for the rigor which they use to protect me as a consumer. They're not going to let just any device, but they don't regulate Amazon so much, so be careful there. So the buzzword here is mechanistic rigor. We need to carefully study the mode of action before we deploy the device into the open market. So finally, the big picture is reactive species. You can think of them as controlled chemical energy, right? You take electricity and you convert it into directable, controllable chemical energy. With just a flip of a switch, you can create reactive environment which can give you the results that you want. Like you can have highly acidic environment without having a bucket of sulfuric acid, for example. So it's very interesting what these atmospheric plasmas can do. And plasmas enable you spatial and temporal control of the environment, within reason, of course, but you can, I've seen plasma treaters that are 8 meters wide that are treating film, they're 2 meters wide, treating polymer film at 8 meters per second. Those pretty insane speeds. The craziest I've seen was with Kodak, the advanced photo system from 25 years ago. They were treating, I forget, it's 17 or 19 layers of photosensitive chemicals that are being treated with plasma that produces light at crazy speeds, giving you super uniform deposition. You have spatial and temporal control with plasma, and innovation here lies in the precision of that control. So you need to understand what is it that you're doing, you need to learn how to control it, and you'll have the most amazing result in the end. And the most important thing here to remember is, although a lot of things I said sound like magic, they are not. They're far from magic. They're a combination of clear understanding of chemistry, understanding of physics, and understanding how those two work together is the secret sauce, not magic. And in closing thoughts, reactive oxygen and nitrogen species, they're powerful. They can do a lot of good. They can do a lot of bad. They're complex, and you need to understand clearly how to work with them, how to tame them, if you will. Control of your plasmas and control of your measurement and diagnostic equipment are critical to deliver the best application. Anyway, I hope you enjoyed this video. I would welcome comments down below on where we should go next. On this channel, I love answering your questions. We did a little vote, and I guess 3 people answered that they want to see more plasmas. I'm happy to. Behind the camera, there are 3 bookcases full of plasma books. So there's a lot we can talk about. Mechanisms, modeling, clinical translation. I'm happy to answer whatever questions you guys may have, and I'll see you in the next one. Peace.